So one of the first things you learn about geometry is that it is based on information from like forever ago. Seriously, Euclid is known as the father of geometry. He is known as the father of geometry. In fact, the type of geometry that you study is called Euclidean geometry, named after him. And so a lot of these theorems that you are learning date back pre-New Testament for sure, okay? And so these are theorems that have been proven for a long, long time. So we're going to talk about 4 different things or levels of geometry here. The first level is undefined terms, which we talked about last time. Undefined terms are basically the building blocks for what they make definitions on. That's your point, your line, and your plane. These are understood terms. They tell you what they are, but they are actually used to then create the other definitions, all right? And so then if you look at the term definition, these definitions that you're going to learn in geometry are based on the 3 undefined terms. And these actually form kind of a foundation for everything you learn. And so it's very, very much building, and they kind of showed it to you in the structure here. It's very important that as you memorize these definitions that you remember what they mean, because later on, when you're doing like a proof or something, these definitions are going to come back to play. The next term here is called a postulate. A postulate. Postulates are assumed to be true without proof, okay? So postulates are kind of understood information. You don't have to prove it. It'll just be statements that are made. And then from there, you get theorems. And theorems are proven. They are shown to be true by a proof. A proof is a logical progression of reasoning. So it kind of builds. You start out with the point, line, and plane. From there, you create definitions. Postulates are understood statements, and then theorems are things that are proven based on these things below. In fact, when you prove a theorem, you really have to go step by step and use something that has been predefined to be able to go on to prove the next thing. All right, and so we're going to look at a lot of postulates, theorems, proofs, and definitions today. And then we're going to do a little bit of an exercise. So on page 12 in your books, we're going to start with postulates. Postulates are understood information. They're not stuff that you have to prove, but it's understood. The first postulate we're going to talk about is the expansion postulate. The expansion postulate says that a line contains at least 2 points. A plane contains at least 3 non-collinear points, and space contains at least 4 non-coplanar points. All right? So basically what this postulate says is that in order to have a line, you have to have at least 2 points. In order to have a plane, you have to have 3 of them. And in order to have space, you have to have 4. And this is actually how you name it when you use your notation. To name a line, you use your 2 points. To name a plane, you use 3. And to name space, you use 4. Okay? So this is just the expansion postulate. It's just basic information. They go on to define basically a line and plane postulates. What the line postulate states is kind of almost the inverse of what we just said in the expansion. But what it says is if you have any 2 points in space, there is going to be exactly 1 line that goes through it. All right, so this is a little bit hard to visualize, but you can literally put your fingers out into space and you could draw a line in between them. Wherever you did that, you would have 1 line that went through them. You wouldn't have 2 lines that go through those 2 points. You would only have 1, all right, that made it through both of those points. But anywhere you put those 2 points in space, there is going to be exactly 1 line that goes through them. That is your line postulate. Plane postulate basically says the same thing. It says you could pick any 3 non-collinear points. Now, why it's important that you have non-collinear points is that if I took 2 points and I have a line, and I pick another point on that line, I actually have the same line. I actually have 2 points, and then I have to have a third one that's off of that line to create a plane. All right. And so when you think of planes, you want to think of papers, right? A paper or my screen up here. It's a 2-dimensional. And the reason it's 2-dimensional is you have 2 points that are on a line, and then you have a third point somewhere off that creates that flat surface, that 2-dimensional surface. So line postulate, plane postulate. All right. Let's look at the next 3. Flat plane postulate. 2 points line a plane. Then the line containing those points lies in the same plane. This is pretty straightforward. If I have this particular piece of paper and I have 2 points on the paper, I would draw a line. That would also be on the paper, right? It's not like my line would go off the paper. So all it's saying is that if you have 2 points on a plane, the line that we just said has to connect those points will also be on the same plane. That's why these are postulates. They're pretty common sense stuff. It's not like you have to define it or prove it. Line intersection. This is one that's going to be used when we start doing some segment proofs. If 2 lines intersect, then they intersect at exactly 1 point. Lines cannot intersect more than once. Those would be curves, okay? In fact, when you get into something called spherical geometry, you start like picturing maybe a globe, and we call those latitude and longitude lines, and they're technically curved, and those actually do cross. But in Euclidean geometry, lines only intersect once because they are straight. They are not curved. And then the same thing with planes. Planes only intersect once, and they intersect at a line. Technically an infinite line, but they only intersect at 1 line. All right? A line and a point not on that line are contained in one and only one plane. Now, this follows with the plane postulate, because if I have a line, I've already established it with 2 points. And then if I have a point off the line, I'm going to have a plane. And then 2 intersecting lines are contained in one and only one plane, and 2 parallel lines are in one and only one plane. If they intersect, they're on the same plane. If they're parallel, they're on the same plane, and that's part of the definition even of parallel. These are actually theorems. So the first group that we looked at were postulates. These are theorems. The difference between these and the postulates is these have actually been proven. So that means the postulates are kind of understood. This one takes those postulates and definitions, and then they go back step by step and say, well, the reason I can do this is that I have the definition of line, and I have the definition of point, and I have the definition of plane that lets me get to this assumption. So they've actually used my prior definition and postulates to get to these. That's the difference between a theorem. They used prior known information to get to it. All right. So let's look at section 4. This is on page 18 in your books, page 18. Some of this is kind of common sense here. A half line. A half line is a subset of a line consisting of all the points on a given side of a point on the half line. Now, there's a difference between this and array. Array actually contains an endpoint, but this is considered a half line. Notice the notation here for a half line. Remember in our video, he showed array. It starts at 1 point and continues. In this one, you'll notice the starting point is an open circle. Think back to Algebra 1 and what open circle meant. Open circle meant that it did not include that point. That's what this means with a half line. It doesn't actually include that point. If it included that point, it would be array, and it would be a closed circle there, okay? But because it's an open circle, it indicates it's a half line. Line separation. Every point on a line divides the line into 3 disjoint sets. So remember, a line is an infinite set of points. Every point on that line can actually divide it. You have the point, and then you have 2 half lines. So you think of it as this particular line right here. We could say we have this point, and then it divides it into 2 half lines. So we could actually write that, the open circle C, and we could put another point out here, to E, and the open circle C to B. All right, and then the third point that it has actually point C. So any point on the line is going to divide it that way. You have the point, and then you have 2 half lines that go infinitely in either direction from that point. All right, some definitions here. So we talked about ray when we watched the video. Ray is a union of a half line and its origin. One way to think of it is that it includes the point and infinitely in one direction. So you'll notice the notation here looks very similar to the half line, except you don't have that open circle on the end. And then they have the definition of between, which seems pretty obvious, but it actually means exactly what it means in any setting. They're a little more specific though. If a point is in between 2 other points, that's exactly what it means visually, all right? But if you write it out, it's between R and S, and they notate it like this, R, P, and S. If R, P, and S are collinear, so in order for it to be between, they have to be on the same line. And if you were to take the intersection of the 2 rays, you should get that point, okay? So if you were to take this right here, this example that they have over here, they're saying if I intersect PR with PS, my overlap should be that point. If my overlap is that point, then it is considered between. Okay, so that is like the long geometric definition of the word between for geometry purposes. So the example is show that R is not between P and S, all right? And so they're using the same exact one up here. How do we know that R is not between those two? Well, if I intersect it, so if I were to take my intersection, R to P, that's this right here, and then R to S, that's actually the same exact ray. My intersection is not a point, it's a ray. And so it cannot be between if it doesn't just intersect at just that one point. All right. Opposite rays, PR and PS are opposite rays if and only if P is between R and S. So opposite rays basically form a line. That's what this is. If you have the same endpoint of the ray, and they are collinear, then they're going to be opposite rays. A segment consists of 2 points and all the points in between them. So while a line is infinite, a segment is, you can think of it as a portion of a line. So if we look at this right here, BC would be a line segment. And you would actually notate it without the arrows, all right? Without the arrows. So let's look at example 2. Determine whether each statement is true or false. It says CD intersected with CA is C. Now notice your notation here. CA intersected with CD is C. The problem here is this right here. That's a half line, and it does not include C. By definition, intersection means that it has to include it, they both include. So this one is false, all right? Union, however, is the line is true. So if I did CD union with CA, I would get the entire line. That one is true. And then intersection, what happens when I intersect those? If I were to intersect the two, ED, this way, the only place they intersect is going to be right here, EB. And that one is true. All right, so you're going to use your set theory and your statements as far as your definitions go here. So if you look at the definitions, a half plane is a subset of a plane. The edge is the line that separates it, and the opposite half planes are the two half planes within that has been separated. And they do the same thing with angles. All right. Angle is a union of two distinct rays that are not with a common endpoint. So two distinct rays that have a common endpoint, that actually makes up an angle. The sides of the angle are rays, so you would list them that way. The vertex of the angle is an endpoint, so you would actually list it as a point. All right. And there are multiple ways to label an angle. Your notation for an angle, as you can see up here, looks just like a tiny angle. So you can label it by the endpoint as long as there's not another angle with it, or you can label it with 3 letters as long as your vertex is in the center of the 3 letters. Order doesn't matter as long as the vertex is listed in the center. If it's not in the center, then you're talking about a different angle. So you can label it with that, and sometimes they'll have a number on the inside, and you can actually name it with a number as well, depending on what they have. But you can label it with the vertex, 3 letters as long as your vertex is in the center, and a number if they have given you a number for it. But you always use your notation here so that I know you're not talking about a point, and I know you're not talking about a plane. You have to actually give me all 3 points, and you have to give me the notation for it. And then you have, this is a definition. This is actually pretty common sense. Interior versus exterior of the angle. The interior is just like it sounds. If it's a acute angle here, you're going to see interior of an angle versus exterior of an angle. So it's basically where they intersect versus the union of them minus the intersection. All right, let's look at some of these.